要不要跟我去？没去，我去过，然后我们可以去玩。
Let's get. No. John. Is it better? Okay. This guy is better. I hope you have a nice long weekend. I don't know whether you have, but maybe some of you have the midterm or whatever. As you can see, I wear long sleeve. It's not because I'm sick or what, but I just come back from the airport. I was where I fly. I went to Singapore and then do a research trip, so I come back. I mean, don't worry. Although I fly, I'm still awake, and then the afternoon problem of deliver lecture. Maybe I may misspoke one or two words, but that should be normal. I mean, today what we're going to do is to continue our journey on random variable. I guess we should be done with that next week. So the idea of random variable is the idea that we are going to simplify our sample space. It's the event because we're trying to measure something, right? And then the random variable represent our measurement or our simplification of our real world, right? For example, is it? Can you hear the back? Right? It's because of the stock market. There are so many stocks, right? So you don't really be able to track every single stocks, but instead, sometimes you care about the stock market index, right? Hang Seng Index, Dow Jones Index, S&P 500, and they represent the stock market. So this is a lot of time we focus on single measurement, and that's the idea. Right, is assign number to outcomes to remind you that probability also a function, also assign number to outcome, but there's some restriction to assign, right? It must be 0 to 1, right? And those have meaningful. There's some axiom to follow, but random variable you can assign any way you want, as long as it's useful for your purpose, right? I think I talk about that, and the main thing is like the distinction is what the support of random variable. What are the numbers that you can put on random variable? Are they discrete or continuous? Right? Can you count them? And if you can count them, it's discrete. If you can't, then it's basically it's continuous. Of course, more technically, right? There's a meaning of discrete, continuous, but we don't go to that. But simply speaking, discrete is you can use the method you learn in the primary school, high school to handle it. Continuous you need calculus, but our course doesn't require the calculus. So basically, just we call an idea of calculus we'll use. We will probably touch it on Friday, or if you have time, we'll do it today. The idea of discrete random variable, right, is give me some outcomes, right? And I assign some number. And just want to remind you this pros and cons twice, right? Then we assign number of head, right? And if number of tail, then you'll be just a little bit slip the diagram. You should be able to handle those. And if continuous is something that very commonly used, and we will just simply use this a lot of times. And just to remind you how we are going to describe a random variable, right? But because of the way, we consider probability, right? It's not easy to describe the sample space and the probability, right? Because they're separate stuff. But when you talk about numbers, then we're likely that you can able to do something more systematic. Like, say, suppose we can describe a discrete random variable by this probability mass function. Simply said, you give the number that a random variable can be the small x. Small x is a number, right? Big X is the random variable, right? And number x can be, small x can be 1, 2, 3, 4, 5, right? And something like this, right? X is either 0 or 1, right? You've tossed a coin once, right? And the probability this guy is blocking the screen. How can I move it out? Yes, right. It's either 1 or 0, right? And it's equally likely, right? P of 0 and P of 1 is 1/2, right? And the other way to describe is called CDF. CDF is adding everything there less than or equal to x, okay? Do note that's less than or equal to, okay? The equal to is important. Okay, the equal to is important. Because it's discrete, it'll be important. Later you will see this equal to is not important in continuous. Okay, doesn't really matter. In general, okay. In the case we consider, it's not important. But for QFN student, should be very careful. This part, when you have a more technical distribution is discrete and continuous and mixed version, then this equal sign will have a lot of thing you have to say, okay? But for our class, for discrete, the equal sign is very important, okay? For continuous, it's not important, but if you study further, that this guy have to be very careful. So this is the illustration of how you do big P and F, big F, right? Big F is nothing, but you just add them up based on the P, right? It's cumulative, it's adding up, okay? I think I don't need to repeat this. I think if you confused, doesn't really matter with the assignment, and then you work on that as well. But I probably should be okay. Okay. I think this diagram is the best to illustrate the P and F, right? Big P will be just coming from assumption, right? And F would be add them up, stacking all the bar graph. That should be no problem. Okay. I guess this not be easy. And the main thing is what we call the expectation and the variance. That will be the main idea that we will be using for the rest of the class as well. The idea of expectation simply actually called average. Okay, it's average. It's simply a weighted sum, right? So weighted by the probability, right? It simply means if you are going to repeat the random experiment in your mind many times, every time there's outcome, and you record it as using the random variable that's common to number, and you run many experiments, you have many numbers. Average of this number turn out to be expectation, right? Because probability, right, is actually a relative frequency, right? So that is the idea, right? This is the weighted average, or simply average, right? Because you just run over that, right? Just to remind you, right? If you toss a coin 1 million times, it's a fair coin, right? If you record the random variable as number of heads, right? Either you have 0 or 1, right? You have 500,000 head and 500,000 tail, right? Head you get 1, tail you get 0. So 500,000 plus 500,000 over 1 million is 1/2. So that is the meaning. Okay. Of course, to remind you that expected value will be meaningful if the adding is meaningful, right? Because this is a mean, right? This mean has to be meaningful if number actually can add up, right? otherwise it won't be meaningful, right? Suppose you, as I said, if you assign head to 2, tail to -1, right? Somewhere real number, the expected value of that would not be very meaningful unless you assign some meaning to it. Okay, they have to be meaningful for this mean to be meaningful, and there's some property of the mean, okay, or expectation that is actually coming from the average, right? If you multiply by constant plus another constant, then this will be same as doing this operation. Just to remember how you understand this is, you imagine X is, they say, the return of the stock or bond or whatever financial instrument, right? And if you buy any quantity of stock X, right, and plus some cash, what is the expected value of your portfolio will be A times the expected return of the stock plus B, right? So that would be the reason why we only in the stock market, right? We just tell you a single stock the price, right? This is the idea, right? You don't talk about there's no difference, it's linear because by expectation. And the variance, exactly the variance idea, okay? And do remind you that this population variance, right? So there's no n-1 stuff, right? You just repeat this experiment many, many times and you figure out the variance. This is a notation. Looks pretty scary if you ask me as a first-time learner, but there's nothing. But just remember the intuition, right? Variance is a squared distance from mean, right? It's a sum of square distance mean, right? Distance from mean, square, and add them all up, right? It's average, right? Because over n, right? So this is expected value average, right? So average square distance from means. And remember what it said is the variance measuring how accurate of the expectation, right? The expected value will be what you expect from this uncertainty, right? But this is measuring how big difference from the mean can be, right? The larger, of course, the less accurate expectation will be. Okay. And the variance formula, because of square, so everything, the formula will be like this, right? Just to remind you how you interpret this is, you invest A in stock X, A unit of stock X plus cash, and cash has no variation, so you don't have to do it. A square, because square, variance square. But you take a square root, which is standard deviation, right? I didn't put it here, but you should know it, right? Take a standard deviation, right? Standard deviation of this will be A times standard deviation of that, right? So that would be very normal. That's why standard deviation is something we care a lot of time, because everything will be more natural. But doesn't really matter anyway. Okay. And this is something that we didn't go through in detail technically because it's an introductory class. So usually focus on univariate probability, right? Even you go to stat department, I think they only talk about this after the midterm. They focus on univariate and then study bivariate. But our class is, we have only one class to cover everything. So there's nothing, that's why we have to kind of skip that formality. But everything would be well defined. But you have to be very careful. What do you mean by you have two random variable? You have to use the joint probability function. Okay. And if you collapse one dimension, it becomes a marginal. Okay. You also can define a cumulative one. Okay. I don't go to detail, but the reason why we need is actually we do need that when we talk about expectation, right? Because of we care about some of the two random variables and some weigh the sum. The reason is that is what you do invest in, say, stocks is X, Y is bond, right? That is something you do, or you have multiple stocks and multiple bonds. And you can see I have only two variables, but this actually hold for any arbitrary numbers, right? So X, Y, C, A, B, C, D, F, G also fine. So this is standard. And of course, you care about variance, right? You care about portfolio investment, right? As long as they're independent, you can just add them up, okay? And this is the main formula that underlies our all the sampling which we discuss in the next topic. You will see the variances add up when they're independent, okay? And later you will see this is the main reason that why we can do sampling is the variance doesn't explode that fast when the sample size go bigger. So that's why doing sampling, collect more sample actually works out to reduce variance. But for this moment, just leave it here. This variance of the sum is sum of the variance. Okay, that is something you need to remember. But the problem would be when we drop the independence, what you will see is you have two covariance. And this is where the key is. And the covariance is indeed what you expect when you look at the finance literature. We talk about portfolio choice, right? You talk about diversification. For diversification, it means the covariance is negative or small, not so positive, right? The covariance is big enough, then actually the variance extend that large. Because for investment, people are risk averse. You don't want to have a large risk, and variance and measurement of the risk, right? So you want to make this as small as possible. So that's why you want to find small covariance or a negative covariance, right? That's the idea, the classical wisdom of you don't put all the egg in the same basket, right? You put different one, right? So to minimize your risk. How to minimize it? It's like this, right? Find the covariance is negative or small, right? And you can see recently there's a lot of, I don't know, alleged scam of the JPEGs, right? And you may wonder why so many people invest in those, right? Even though it looks like not legit or what, but the one reason is because the financial market these days increasingly have high correlation, right? You can look at Hong Kong stock market is highly correlated to China economy and also closely related to the US economy. So you don't really find good investment that is uncorrelated stock market, right? Local housing market is, and the stock market is closely related, right? So actually people why invest in cryptocurrency, right? For some reason is they want to lower the covariance. I mean, there's some reason to explain why the JPEGs is such a big event. I don't know whether they're a scam or not. I'm not police, so but you can see that so many people are invest on those. There's some reason, right? It cannot be all people are some. Must be some reason behind that as well. But anyway, so today we'll finish this before the break is to give you several useful discrete distribution. Okay, they are very useful for the subsequent analysis, but they by themselves is very useful, as we will see in the example, because if they are the useful model to model uncertainty, as you will see. Okay, and the first one is uniform. I guess I mentioned this is starting point when you try to model anything. If you don't know, you start from uniform is the best. Although we don't talk about this in the advanced courses, we talk about basic learning, updating. You always many times start with uniform, and you keep update, and you learn. Okay, this is the thing that the starting point. So and every outcome is equally likely, and that will be a good case if you have the possible outcome is a huge space, right? You don't have a good knowledge. This is something you would do. Okay. I don't think this leads us to describe because we know very well. Okay. And this is probably the main starting point of the journey of the probability is what we call a polynomial trial or polynomial distribution. Is we do a single random experiment. Either you call success or failure or head or tail, depends. And we will say probability success is P, and failure is 1 minus P, right? With number of success, because you only do one, it will be 0 and 1, right? If we natural and extend to binomial, number of success will be more than 1, right? Now it's 0 and 1. And obvious reason by definition, P of 0 is 1 minus P, P of 1 is P. This is the definition. And by the outcome is very normal, right? If you ask people, do you like hamburger? Do you like hot dog? Do you like spicy food? Okay. Do you like the stack cars? Right? Do you like accounting? Whatever, right? There's many things. It's yes, no question, right? And probably I explained in the last class. This is a condensed way to represent the binomial distribution. You don't have to do that, but this is to connect yourself with the binomial. Okay, this is more natural. And the mean will be P. Okay, and the variance P times 1P. The mean P I think is natural. That I think there should be nothing new there. Variance would be need some explanation, as I mentioned. P is going to be very small, right? Then it's likely that you are never successing, right? Most of them is going to be failure, right? And if you run this data, right? If all of them are failure, then it's almost close to 0, right? Because you have a lot of 0 and some of the 1, right? And the variance will be very small, right? Because most of them are 0, the mean is very close to 0, right? So the difference from that, the variance will be close to 0 as well, right? Same idea when P goes to 1, right? But when P is 1/2, the variance is large. Why? Because your mean is 1/2, right? Expected X is 1/2, but a lot of data are from 0 to 1, right? So every observation actually, the difference 1/2, right? It's a large. So that's the idea. And it by itself is do not have too much application, but the application lies on this one, binomial distribution. Okay, so this is just simply repeating the binomial n times, and each time is independent. Okay, and independence is important assumption, and you may find this useful or not, but sometimes it violates. But this is the starting point. You will see this is very useful, and consider each one has success probability P. The random variable is number of success. Okay, so this means that I don't care the order of success. Okay, I just care total number of success. Okay, so that is a simplification, right? Otherwise, you have 2 to the power n in the sample space, right? But you simplify it as count number total. So we just the support will be 0 to n. Remember, 0 is there, okay? Because you have all failure is possible. And as I explained in the next technical slide, this is the probability function, right? The reason you have this, let me explain again, is suppose you have X success, right? First of them are successful, it's P times C up to raised to the power X. And the rest are failure is 1 minus P raised to the power n minus X, okay? It's all success and all failure, right? But this is only one way to have this, right? Because you can have failure first and then all the success, right? And this other way, right? But you can also mix and match. So how many things you can do is NCX. How can you think about this? You think about n balls, okay? You ball have a number from 1 to n, right? If you draw, now you only draw X number of balls, X balls, right? That means if you draw ball number 1, the first one success. If you draw number 2, the second time success, right? Or you only have X balls. So this is the idea. If you don't get it, doesn't matter. I don't think I get it the first time I do it. So just remember the formula. At the moment, sooner or later you will realize what does that mean. Okay. At many times for statistics, it always takes time to understand. Okay, it's okay not to understand at the first moment. After a few trial, then you know, right? It's like a blind marriage, right? Just like in the old days, right? one man and woman, they never met before they get married, but sooner or later they know each other, right? So that's the idea, okay? And you have to get married with the formula anyway, right? So there's no way you can do anything, okay? And mean and variance is just multiplied by n. The idea is because they're independent, so mean just multiply by n, variance just multiply by n, because variance, the sum is sum of the variance, right? Because this random variable binomial is just sum of the n binomial, okay? If you want to do that, but if you don't worry about it, this is that proof that you can actually prove it, okay, from the first principle, or we can rely on the independent property, but we're not going to prove anything. So this is what we have, okay? So this is the graph. Maybe it's good to talk about example that motivate why we want to do this, okay? And I think we stop at this point, okay? The next slide will give you the actual application, okay? This is the warm-up. So the question here give you is a restaurant owner from historical data, 30% of the customer like spicy food, okay? For marketing research. So this is the 30%. So the question would be, now they expect 5 customers coming to his restaurant, okay? And asking 2 of them actually like spicy food, right? And this is simply binomial, right? Because it's just 5 people is random. The customer are not really related, right? And so we have n is 5, because out of 5 you have 2 of them, and 30% of the people like spicy food. This is probability, right? Will be 30% of people like spicy food, okay? And probably you will say, so what, right? Why this related to any decision making? The idea is following. So this is the real application, will be the following, right? It's asking the restaurant owner, because in the morning he need to buy some spicy food ingredient, right? Because spicy food need to be pickled, put in the flavor, put in the fridge in the early morning, right? You cannot just put spicy food, right? You have to spicy there, sit there for a few hours, right? And that's the idea, okay? They want to see no more than 2 people like spicy food, okay? And do note that the no more than 2 is include 2, okay? No more than 2, okay? And the reason why we want to care about this is, do the restaurant owner need to prepare 3 or more quantity of the spicy food, right? Because if the probability of no more than 2 is large enough, then he will be pretty safe, only prepare 2, okay? Of course, there'll be some chance that some customer may be unsatisfied, right? But you have to calculate probability, right? And then you can do decision, right? You can calculate cost and benefit analysis, but the first one you have to calculate how likely that this happen, okay? And it's asking less than or equal to 2, okay? That means that I want to have p equal to 0, p equal to 1, p equal to 2. And you can plug in the numbers, okay? And turn out to be 84%, okay? And that means that if this is the case for the restaurant owner, only prepare 2 will be enough. Okay? Of course, you can prepare more, but if you are going to be optimize your inventory, right? This is what you do, right? So this is a business decision, right? Remember our class, right? We're talking about business decision, right? In statistics, okay? So this is how you make decision, and this is very normal, right? You can almost adapt this to many kind of situations, okay? And I think probably you will do some exercise for your assignment. This will be related to this kind of application, okay? And then a bunch of proof to show you how you can prove all this. But as I said, this class is not math, so I'm not going through the math. If you have any difficulty reading the math, let me know during the break, and I can explain. But I'm not going to go over the math here. Let's save ourselves from the math. But is that okay? You understand the meaning of this, right? Because you can model a lot of stuff by binomial, okay? there's n thing, each thing you know how likely it is from the data, right? Then you can see how likely, how much thing you need to prepare, and so on and so forth, right? And well, you can imagine this also the case for say, right? This you can imagine this also useful for public transport company like the MTR station, MTR company, right? Maybe 1% or 5% or 0.5% of the train can go wrong every day, right? Then you have to prepare how many extra train to be there to make sure that 99% of time you have there's no shortage of train, right? Because you have a spare train to be there. That's the same question. Okay, so this is very useful, and that's why engineering people they do this all the time, right? Because like the question would be like, why the plane you have many engines there, right? If you have 5 engines, if one engine fails, it still works out, right? I mean, you look at the Elon Musk, their rocket, right? The rocket have many small engines, right? And then even if many of them fail, actually will still work. And the calculation is like this, right? Each engine will fail, and you what make sure that how many engine minimum will still have enough thrust to get out. This some engineering will be very important. Of course, same for business, right? You want to make sure that as hotel management, right? How many rooms will be there, will be enough, right? So on and so forth, right? So Poisson, okay, and actually we see this Poisson is actually closely with the binomial. Okay, it's a binomial. The case when n go to very large and p is not big enough, and you will see this is look at the usage first because that would be last bullet point. Is to model the arrival number of people. Okay, it's over a period of time. So this is very useful as a business decision. Okay, so let's see why binomial can extend to time idea. Okay, so Poisson, and those who understand, who try to study finance, in the future, actually a lot of process over time is measured by Poisson process, and this is the foundation of that. Okay, you have a dynamic stochastic process, and you model things by Poisson, and this is the idea. But this will be a 4,000 class for stat, but not our class, right? We have a very simple class. So how the binomial with the time? The idea is very simple. Look at the first sentence is partition the time into n interval. Okay, you consider time interval. Okay, 1 hour, 1 day. Say you cut it into say minute by minute, right? Or second by second. Then a many interval, right? Suppose an hour, right? You can cut it into many seconds or many minutes, right? And you can imagine each minute or each second, right? Then maybe something happens, right? Maybe your restaurant owner consider how many customers may come in, or your insurance company consider it's likely that the accident will happen, or your modern stock price, likely the price go up or go down, right? And each one have probability P, right? And it's independent, right? And X is number of success, right? It's number of a customer is coming, number of accident go in, right? And the support will be 0 to n, the same as binomial, right? There's nothing new here, right? Same as binomial, okay? Why it called Poisson? I think it's because I remember correctly, it's the guy of Poisson actually figured out that when n is very large, okay, and this guy is very complicated to calculate because they involve factorial and stuff. Turn out that he simplified to this much simple form. You still have factorial here, okay? But this e to the power n, you don't have to calculate the NCX, and this e to the power whatever is you can look at the table in the old days, and probably if you don't study math, what is e? E is what we call a natural number, is 2.713, just a fixed number, okay? And why this guy go to this is beyond the scope of class. If you study M1 or M2, you know it, but it's just a natural number. It's a involve a limit But anyway, we don't want to talk about those. And if you learn compound interest, it's actually the same idea here. But we are not going to that direction. If a compound interest, continuous compounding, but it's not related to us. Okay. And you will see the example how it works out. Don't worry. Excel can do all the calculation for you. Okay. Regardless of exponential, EHP, or this Excel can calculate directly. Okay. So everything, don't worry. Or in old days, actual table. Okay. But now we don't need to worry that. Okay. It's simply just to remind you this is just binomial. But you consider as an interval and you cut time interval very small. Okay. And success implies someone comes in, right? And we cut the interval so small that only one guy can come in. Okay. Or zeros. Okay. So that's the idea. Okay. And right. And the lambda will be called, usually the lambda is called NP, right? And N is large, okay? And P is small, it's the constant, okay? It's a rate, okay? And you notice the power function like this kind of formula, okay? Which is you always find in the textbook, okay? It's this formula give you. And one interesting thing turned out to be different from binomial, right? Binomial is NP, right? And NP times 1 minus P, right? But this one turned out to be because we said P is very small, right? That's why this guy is gone. So mean and variance are the same. Okay. So for Poisson, a very special case, the mean and variance are the same thing, lambda. Okay. Not going to do any proof, but we will go to the example. Okay. Before that, we look at the graph. Okay. And when lambda is not that large, you notice it's like a bell shape, but a long tail. But if you figure the lambda get larger and larger and larger, you will see it is close to a bell curve. Same as binomial when n is large, okay, and you look like a bell, okay. Poisson, the same idea, okay. So that's why later when we look at the bell curve is very useful, because when you consider when you consider one day maybe as a Poisson, but consider 1 month, you can use normal, right? That's why the stock market, if you believe that whole 1 day, or insurance company, you think about the arrival of accident is a Poisson, or a stock owner consider customer arrival is a Poisson. But on the long enough horizon, bell curve would be the way to go. Okay, things actually get easier. But to be exact, we'll use Poisson anyway. Okay, so this example that is very useful, right? Because you want to model number of customer, right? And that will cater to make our business decision, right? The question is number of customer that arrive each hour follow the Poisson. With mean 5, right? Was probably the exactly 2 customers arrive in the next hour. Okay. Again, this is warm up. I think we also asked. I think I asked in the assignment, but you should be able to answer the same question. Was probably less than or equal to 2, right? And then you can decide how many staff to deploy in your shop to cater customer need, right? This is if hotel management is what you need, right? You have to figure out how many customers are coming, or restaurant, how many staff. You have to make sure that the staff is there, right? Simply you just apply here mean of 5, so lambda is 5, right? You just put the number there, right? Then it should be there, right? Because the idea is right here is e to the power lambda x factorial, and lambda being 5, x is 2. Okay. So this is exactly what we do, right? As an auditor, you also can think about this, right? Because you think a lot of things follow lambda. The production plan, how the production goes, usually follow how much product they're doing is usually follow Poisson, right? Because a lot of things is a good approximation to the real world, and then you can test whether go to audit, you can see whether you go to do things there, right? Stay there for an hour and check how much product they produce, right? And then that's the Poisson idea, right? And right, if that's what behind. Is that okay? So these are actually very useful thing you want to model business situation, right? How many people you're coming, and then of course you can think a lot of application as well. But these are the basic thing that actually people use it, and there are more. If you look at textbook, look at elsewhere, there are many. Okay, and everyone who learn probability would learn this thing if you learn probably college level. So there's nothing very special here. I picked these two for you. Okay, and the proof I omit because I don't think it's important. Okay, and this is to show you why Poisson and binomial they're related. Okay, but I'm not going to do the proof. Why I said when n go to infinity, very large, and p is not that large. This is a proof. Not a proof, but a informal proof. But that's actually require real proof. But we are not proving anything here. Okay, this informal proof. So after the break, we'll talk about this hypergeometric, and this is related to sampling with replacement. So without replacement, this actually do the audit. Okay, you go there and pick up things and see whether they're defective or not. Okay, and binomial is sampling with replacement. Okay, but when the sample size is large, binomial will be a good approximation of hypergeometric. Okay, and this is a realistic one, although difficult to calculate. Okay, this is quality control. Auditing will have this probability. Okay, if you but we will talk this after the break. Okay, and let's have a break, and then we'll talk about this. Okay, in the meantime, if you open the U reply, and then you can ask me. If you don't want to ask me a question, you can ask in the U reply. We will answer a question in the U reply. Okay, let's have a break. And I open the U reply, and then if you have any question, please ask in the U reply, or you can ask me. I go around. Okay, let's have a break. We will resume now. It's 11:38. Okay. Scan.
It's LOL.
LOL. Is it LOL or what? 我呢個王者榮耀 係。Okay, so any question? Yes. Hmm. 負數嘅話，咪0.幾咯，唔係咁計，即係話你個 譬如話你個 return 係
他这个嘛，写的都很清楚。
咬晒落，swap 係 swap 晒，係為咗個平衡。因為為咗個人咧，就係就係喺度我也覺得如果入咗聲尾就唔會。我是那个，用中文教，今日啲上堂點解我都唔知嗰時講中文教，有啲基本上所有都係 Cantonese 㗎，都冇晒。但係只有一個就係咯麻煩，所以我哋係我係諗住翻中大教嘅，我哋講廣東話開手。總之我嚟到係我都唔可以講廣東話，我都係中意用廣東話教，廣東話教係個關於艾德公司咁我讀書嗰陣時係中英夾雜咁啊，香港就係英文嘅 slide 嘅用英文講啊，但係。係啦，你有中文 slide 係咯，咁多呢啲都好 set 嘅嘢啫，攞任何一本書都一樣。如果擺多啲場嘅話，你 N 就分開 N 次， 有時就分開個時間開，就開做幾每個鐘開6分鐘，每6分鐘都有啲冇人。
对呀，还要把你和尚的那个
消化的方面，至於點解咁樣，佢整個人係佢想話，你其實嗰啲係 combine trade 嘅個三嚟，呢個先。上半年俾兩有冇試試？我120萬左右，可以我係就俾兩
燒有对，确实是。有冇嘢同我對講？我要我覺得佢重全班会员啊，我们中还也挺那个靠我那个会有专属晚饭是我们别人到了那里6点没有晚饭，没有然后我们不想吃吧，然后结果到了之后呢，我又说不想吃。主要是你仔嚟一嚿飯，對個預期咪一唔山咯，係發覺夾係咯，我認同。
我對 DSME 都係但係如果入咗翻到咁主要唔知咩陳龍 十一至十三數
即係有，即係簡單嚟講就
这个叫
十三日都我今晚咪聽日至11日。
骗子，
可以有快方面嘅，
这个也是。
我哋
这个也是。
都可以
呢個狗之後就血戰 GCC， 之後
我有諗住都幾想學到話，即係如果 N 出咗 S
所以個 M 好大聲，個 M 好大聲。
我係咁樣嘅情況下，
係啊，我想個 M 好大，M 嗰個 N 個 N 呢個又係俾真係
真係
呢個情況去分別。
係啊，都係我哋
是我之前没有问。
搞唔到賬號嘅啫。
即係佢睇小姐，係咪？
我驚佢有人起個底啊！算啦，個人
係免費嚟嘅，係啊，你睇
Yes，
咁為什麼唔接受？你使唔使急多幾？
The answer is what we call you learn 3, 4 research 你學過呢個2 + 3 multiplied by 4 you can multiply each number and add for the distribution property of multiplication. Oh, that's addition property. That's come from learn from the primary school math, right? 因為E 等於 B.B.A 但係冇啊，
係咪直接呢個 M.P 嚟㗎？將呢個字
呢個 district 咧，我哋之後呢個失貨呢個呢個
I also don't really.
我哋嗰陣時有講過數理都知道係好唔係，要證明可能好難，但係你要知道係咪每個範圍啱 呢個就話其實呢個係細嘅同細嗰度啫嘛。呢個就下邊你每一個人就選出個人出嚟，有30%佢中意辣嘢噶嘛。咁咧5個人，不過2個人係有食辣嘅咁咪。都未係有最後㗎。冇特別，我真係冇親嘢第招檔嘅。冇人叫你背抄嘅。考試咪繼續抄咯。你帶住筆記或者帶住筆記。我份 book 就梗係唔使抄㗎啦，你抄你冇問嘅，我問你啲咪即係自動送分。咁你試下問下想分啲嘅咧，唔係好難嗰啲，咁可能。
我都講佢哋3個好正氣嘅，
我盡量大家簡單。
我就得
借多啲
成日都唔得，點解佢叫你用成啊？你文嘢面學校的我成日要講㗎。喂呀，我諗住同你一齊。
英語啦，如果唔係打計死啦。呢個咪就係波嚟嘅嘛。我一費大家自己抄嘅，我諗下。
你可以兼你個 program。
咁呢個出意外。嗱，容易都唔係好大㗎，之後真係睇書咯。
做咩啊？
應該唔會咁難嘅，不過你如果都做話齋明到嘅。
你可以翻嚟去多次，可以做多所嘢。我廿八號嚟。挺酷的，就是不会，而且会拿见到这个吧，水氣食真係我們的跟他比例
I guess it's time to resume. So I end the you reply and see what question or comment we might have. Yes. So if we start going before we end, a little bit. Okay, I think today we also have very fun. Can you see the? I think can see, right? Anyone know the answer? I don't know. Sorry. Oh no! So now you get the joke. So it looks like this. Okay. Those who want to take picture can take picture. Because I saw some take picture, so I just go back. Okay. So, I think it's good. Last time we have a joke of McDonald's. And now we have a mixed joke. Okay. So the question is, I don't know the answer as well. It's okay, then let's open. Okay. That is a very good one. That's a good one. I like this one, yeah. We'll give it. Yeah, that's a joke, yeah. Formula so hard to remember. That's okay. That's no remember formula. Open book. Okay. This class open book. Okay. I guess it's a joke, right? So another one. So as you can see, right? So let's open the answer. Oh, fair enough. Fair enough.
Okay.
I'm so sleepy. Okay, nothing. So this course is so difficult. Yeah. Sorry about that. I mean, I guess the question is that there's a lot of information there because there's a lot of formula, and it'll be easier if you do the assignment. That you'll find easier, definitely, because of application style. And yes, this is a different lambda, right? Because this is what we see. The question is different lambda in the shape, right? You can see when lambda is small, it's like the long tail, and when you have a bigger lambda, it's more symmetric. Even bigger lambda, it's become very symmetric. Okay. I hope this answers the idea of the shape. Okay. And how detailed you want stuff to be? Except open book. So you bring whatever you bring. No need to remember. I mean, if you need to remember where to find the formula, then it's fine. How detailed I want to be? I think my slides would be the thing that is a optimal way to write. Of course, you can write more or less, doesn't really matter. As long as your answer is correct, this will be fine, right? And you can write ... if you has 2 minutes to write. Okay, as long as you illustrate to the TA or the grader, it's clear that you know it, then we give partial credit, right? Because if you get everything right, even if the final answer, probably we're able to give you full credit, right? But if you don't write anything, you just got the wrong answer, though, we can't give you partial credit. So I suggest you write in full. Oh, wow. Okay, some NX means P. NX is NCX. It's N factorial over X factorial. times n minus x factorial. You look at the chapter 2, topic 2, for that one. So this is, let's go back to this one. This is just, this guy is just means n factorial, x factorial, n minus x factorial. Okay. And E is just a number, 2.713. Okay. It's always X number. So let's see what we have. Okay, so far it's okay. Yeah, everyone got it right for today. That's good. 5 is
Oh my God.
yeah, seems everyone getting all right. There's no problem. X factorial, yeah. I think that's fine.
It means no.
So I think today most people find it very hard to follow. I guess it's we have a lot of information. That's for true. I mean, I definitely understand that part. Because we are just introducing the idea, but we don't give details. So just the hard part is, I think the hard part is understand what do the formula means. Okay, and I guess is the main thing is you can see you would like to remember the thing in the purple box. That's what we use, right? You look at the mean, the variance, the probability. That's the main thing we do. Okay. And later at the end of this topic, we'll do Excel. So everything can be done in Excel. Okay. So but you have to know which scenario apply which formula. Usually you know what formula to apply anyway. I will try to give you in the formula what situation you're using in the question usually. Okay. But so that shouldn't be an issue there. But you know why they're applying. Okay. So I guess it's go to this last one for this quiz. Okay. So binomial, remember, is we have n items. Okay, we can add up, we pick things out, right? Each item has probability sets, right? And but you can consider this the same as sampling without replacement, right? Suppose you have doing an audit, you have n object, right? Out of np of them, n times of them are not defective, right? You want to calculate probability of defective items, right? And when you say replacement, we do it and put it back. But here we focus on the case actually related to quality control, or what we say the auditing. Okay, imagine the following: you go to a warehouse, and the client told you the n items. Okay, and they tell you, right, out of n item, 8 of them are good. Okay, very good. Okay, that means the bad item are n minus 8, right? So the idea is very simple, right? So the idea is, right, you have total n of them, right? And you are told that, okay, 8 of them are good. So 8 of them are good. Okay? And that means that, right, n minus 8 are bad. Okay? In total, the n. Okay? So this is the information given by the client. Okay, they say in the statement, right? And 8, right? Or you can say someone tell you the machine, right, has a defective, maybe out of 100 product, okay, that 1% of product is not doing well, right? And the n is 100, a may be 1, n minus 8 is 99. Right? If you consider A is defective, depend on how you call it, but this is the idea. Okay, this is the data, and this is given to you. Okay, and the question would be, we are going to draw X out of it. Okay, so what we're going to do is we will trying to take small n item. Okay, n item of that. we're trying to ask what probability X of them are picked. Okay. Probability that pick equal to X. Right? X is a small number, 5 or 3 or 4 or 1. Okay. Of course, that means that n minus x is cross, right? Because either you take or cross, right? Maybe I should not use cross and take, right? Because they're a little bit confusing. I use I use another. Maybe I use an. What am I doing? Maybe I draw it in another picture. I use why it's not responding to me? Oh yeah, I see it's not responding to me. Okay, let's try again. So suppose I have an object here, right? And I have right. Among that, I have a smile. Okay. A smile, right? And that means that I have n minus a not happy. Okay. And what I'm going to do, right? Suppose I am a KK park, right? And I go to grab people. I grab n people. N people. Okay. The question is asking probability that I have X smiley face and M minus X sad face. Is that clear what we're doing? This hypergeometric, right? Because this is exactly what you think, right? The client tell you A are the good and M is bad. You're going to go to the warehouse and pick up N item and try to check it out, right? Asking X of them are good and M minus X are bad. Is that clear what we're doing? Okay. So if you put it back, once you pick it up, put it back, then you become binomial, right? Otherwise, you don't put it back, then it's hypergeometric. Okay? Because it is a binomial with n over p is n over a. Right? That's a over n. If you put it back, it's a over n as binomial. N is n, it's binomial. Okay, if you put it back, okay? So later you will see where n is large. Binomial is a good approximation for hypergeometric. So that's why binomial is important, right? If you do sampling, whether replacement, if you go to the warehouse to do quality control, and it's large, doesn't really matter. Okay? But this is the idea, and you do quality control, you do audit. Is that clear? Is that clear what we're doing? The example. Is that okay? Yeah. It's clear, the use case is clear. What you're doing. Okay? Now go back to here, right? N item, big N item, A of them are good, and you take small n item, X is the random variable number of good items, okay? And combinatoric style with this guy, okay? Why? The denominator, because big N, you choose N, so N over N, right? And A of them, you pick X of the good one. For bad, you pick M minus X. So that is what it is. Okay. And of course, you don't really have to, remember why the formula is true. Is the formula. When you do sampling without replacement, that's what you do. Okay. And you will see usage case. Okay. So obviously n is equal to 1, then it's polynomial trial because it's two ones, right? And you can easily see that when, as I said, A over n is P, right? If you have binomial, right? Because when big N is, when you look at the variance, when big N is large enough, compared to n, this guy is very close to 1, right? So that's why I said when the hypergeometric, when you have a very big n, right? Doesn't really matter anyway. Okay, because it's a over n is p, right? This is p. This is 1 minus p. Okay, and you don't have to understand why, but this is the formula. Use it. Okay, I think when I first learned that, this is the distribution. Okay, and actually some of you asked, okay, we just learned 3 of them, and indeed, if you try to look at Wikipedia or other textbooks, there are at least hundreds of this kind of stuff, because there's many things that you can apply to your scenario. You just pick the one, and we just introduce some common to you. Okay, and unless you are a mathematician, you don't derive new thing. You just see which one apply to your case to apply. Okay, the many types you can fit. You can fit your application. And when you use it, look at Wikipedia, look at the textbooks. They will tell you this kind of thing will fit what and what parameter you want to fit, right? In this case, you have small n, big A, and small big N, right? To fit your use case. So just take a look at those, and you fit in those, and you're done. Okay, it's a toolbox, right? You don't really care about why it works, right? Just like the app, right? You don't need to understand what the app internal working. You just know this app do this function, this app do this function. The only thing you need to know is go to the app store and figure out what to pick up, right? The same idea. I mean, we just tell you the basic several thing here. Okay. And you will see the use case. Okay. Okay, this is explanation of that, but you see a lot of complication, but you somehow see it's like a bell curve. Okay, if things are large, then bell will be there. Okay, so this is the example. I hope that will give you the idea. Okay, and you can imagine that a company, they claim in the office that 30 computer, and 4 of them defective, means that they want to depreciate that thing, or they want to write that out from the assets, right? As auditor, you want to check they're right or not, right? And what you're going to do, right, is to calculate this probability, right? You take out 6 items there, and tell that 2 of them are defective, and you try to see how likely this outcome, right? If this is unlikely, right, then you would think, okay, my client may not be telling the truth. I need to do more sampling, right? But okay, how to do this in the proper way would be left for hypothesis testing. Okay, but our course will not cover that advanced. Okay, if you want to do this type of stuff, actually doing all the using this, you have to study, I think 2,000 will not cover, I think 3,000, 4,000 level. But you can see the idea what's behind that. Okay. But as here we see, simply we have A, small n and small x. Okay, just plug in the number here, right? Because the formula, if you recall, okay, you just copy the denominator, just pick n, choose n. Right, and out of A, X of them are good, and n minus A, n minus X. Okay, and probably ask me why I use this complicated notation, because this notation is used in Excel. So actually, I do this because Excel uses this notation, so I just follow that. Is that okay? Any question? I mean, just apply. I don't think there's nothing there. The only thing only you have to check out why this is hypergeometric, because you take things out. Okay, and I guess in most of the time I will tell you in the assignment, you know, actually I'm asking hypergeometric or Poisson or binomial. Okay. Okay. So shouldn't be an issue. Okay. Is that okay? So these are the proof, but I guess none of us need the proof anyway, unless you want to do math. Okay. But just basically introduce you some common usage case of random variable, right? Because random variable, you have discrete, you have many numbers, we record, and then you see when to use what, right? And if you try to think about an experiment, each experiment either success or failure, binomial outcome, you use binomial distribution. And some of you in the break ask, what happens if you're more than 2 outcome or 3 outcome? Yes, there is what we call multinomial, but it's not within our syllabus. You can do that, okay? I mean, because statistics have been developed for so many years, what you have been thinking would apply in your case will actually be there in Wikipedia or some textbook. We just tell you what can be done, okay? And Poisson is also common when we try to model arrival of stuff, okay? When you think about arrival, Poisson. Number of success, you think about replacement. With replacement, then will be binomial. Without replacement, then will be hypergeometric. That's it. Okay, that's the thing you need to remember for our case, right? And then many more and more. But is that okay? Is that okay? Anyway, you do assignment, then you have a much more easier mind when we do it. Okay. Before we continue, is there any question? I'm pretty sure since many of you write number 3, so I slow down a little bit. You ask a question that I just talk about it again. Is there any particular thing you want me to cover again? Okay. So continuous random will be the same. We'll just tell you what kind of distribution, what are the use cases, and that's it. Because we're not going to derive any proof. Okay. The only thing we need to be a little bit more careful is how to describe a continuous random variable. Okay. For discrete, it's very simple. X equal to some number 1, 2, 3, 4, 5, usually integers, right? And continuous random variable is, imagine decimal numbers, right? Money, temperature, stock price, stock index, inflation rate, all these number continuous because decimal numbers. Okay. To do that, usually, from math perspective, this is still well defined. Okay. This is just a useful way to define stuff is probability that x less than some number, right? We will later see it's easy to define the probability that the rainfall is less than 50 meters. Okay, less than 100 meters. That will be easy to say. Okay, because the probability exactly equal to a certain number will be very small, right? Because you're continuous, right? The many number, right? So that would be very hard. Okay. So how do we do about that? Okay. So here comes a very funny notation. If you never learn calculus, I put there because I can't really skip that part. Though we never ask you in the exam or what, but we need to write down this is something weird. This is something weird. Okay, if you never learn calculus. Okay. So if you still remember, when we have discrete, we have something like this. This guy is summation, adding all the P of X, right? P of Y, right? For Y less than equal to X, right? Because that is what do we mean by less than, right? And in calculus, when you try to do a summation, it's just integration. You have to write in the other way, we call integration. Okay, this is actually, if you learn calculus, this is actually S, right? And if you learn math, this sigma is actually also S, because this is sigma. It's a Greek letter of S, right? Sigma. It's big sigma, Greek letter. Okay? Both of them are summation. It's adding something. Okay? And you will later see this F, the small f is called density. The idea actually borrowed from physics. Okay? Borrowed from physics. Kind of like the density and the mass idea. Right? If you learn physics, F is actually a mass concept, and density, right? Aggregate density is a mass, right? But we don't want to go to calculus, okay? But what we need is redefine something like P, right? P is what? The probability that x equal to that certain value, right? X equal to 3, x equal to 4. But how does that work in continuous case? Okay, is we have this idea, f of x, okay? And it simply means that idea is like the probability, right? In x is between x and x plus delta over delta. Between a small interval over the size of interval is the rate. Okay? And that's why that's become calculus, right? Because differentiate the rate is a slope. Okay? So probably is still kind of crazy, okay? But I reassure you, let me go to a graph that will make us easier. Okay? Remember we learned discrete where px and f of x. Right? The discrete case is we have some bar right here, different color. Right? We have light color like this, right? Red. We have blue. We have blue, right? And we have green. Right? And then we can write this guy, right, as green plus blue plus green, right? And then we have red plus blue plus green. Okay. So the same idea goes on here. Okay. Is the continuous with the same idea. We have F and with F not join. Okay. So you will later see I would put the example of bell curve. Okay. The bell something like this, right? When the bell curve is something like this kind of stuff, right? When I call bell is actually this guy. It's the bar chart, right? The histogram. Okay. Sometimes actually we call the density plot. Okay. It's this guy. Okay. It's the bar chart. Okay. Small f. Okay. And this one is what? This is 0 to 1, right? It's again, right? 0 to 1. Same idea with something like this. Okay. And say I take a value, this is something you need to remember. If I value x here, okay, this is f of x, right? And that means that integration, the notation here is the area from beginning up to x, the size of this area is f of x. Okay, so this is the calculus idea that we will use. Although we don't prove it, actually the fundamental theorem of calculus I mean, if you learn it, but if you don't, doesn't really matter. This thing we need to remember. Okay. Same as the above, right? The left hand side add up all the area on the left hand side, on the left, right? That's what we're doing, right? Everything, the big F is stacking up the bar charts, right? So the same idea here. This value is stacking the area. Is that clear? I mean, I'll draw it maybe more clean. So you have a green here, right? And then you have a blue here, and then you have a red here, right? So you just stack the green, right? Stack the blue, and stack the red. Is that clear? But we have a continuous, but the same thing, okay? And if you learn calculus, right? Simply this integration and this differentiation because of slope. But we don't use calculus. We just use a graph analog. Is that clear? Of course, this is complicated, I'm pretty sure, because this first time you learn this, not easy to understand. Because, but if you understand how big P and big F in discrete, actually carry down to the F and the big P. Okay. Or like this one. Maybe I should take a picture as well. Maybe I should add to the slide sometime. Yeah. Okay. So I hope this would give you an idea why this is true. Okay. And I think I give an explanation. If you want, you can read that. Okay. But I'll give you the explanation for that. Okay. The very technical stuff is this continuous. The only thing is to be cared for QFN student. The probability that random variable equal to any number will be 0. Because you just imagine, I'm going to throw a dog over there, right? For a tag over there, and I hit a particular point with 0. Right? It is not saying it's not possible, but the maximum we use is 0. Okay, it's just the measurement is 0. It's not exact. Need not be 0. Probably 0 is not just impossible. It's just like the way we measure it is 0. So there's a measure theoretic idea. 0 doesn't mean actually 0. Just like, let's imagine use a ruler. Use a ruler to measure the cell size of a cell. Then you can't measure it. It becomes 0. But cell is consists of some length, right? But if you use a smaller ruler, then you can measure it. But the ruler we use, we consider is not small enough to get it. So these, because of 0, they're all the same. Okay. Now I'm going to talk about that. So this last slide, okay, is we got a crazy stuff, okay, and this is no different from what we learned from discrete. Okay, and if you learn calculus, this is the way we define mean and variance. But it's just the same idea of if we do this experiment many times, we got many numbers, right? Average those out is the mean. Same idea. Okay. Although I write blue, we never use it in our assignment, test, whatever. I just put there because we have to define something, right? Otherwise, I can't put it in technical because this is what it means. Right? But this is no different from just the same thing. Okay? Same thing here. So just X times the probability. Okay? And the same here is just same as this guy, just this guy. X minus EX square PX. Same of discrete. Okay? If you learn calculus, this is normal. Okay? But for QFN student, please know how to do integration. You do integrate by part as well sometimes. And that you will do variance and expectation. Okay? I mean, nothing in our assignment will do anything integration or But you can look at the proof and see how they're being done. Okay. Okay. I guess I have to end because I think it's time and also I covered too many today. So 1 minute early, I don't think you complain. Okay. So we'll see you on Friday. In case of any question, please ask me. I see you on Friday.